Let's go ahead and begin. A week from tomorrow will be our first exam, so some of you are already thinking about it, and that's good. I haven't written it yet, so I don't know what will be on it. It will be delivered to you via Learning Suite. It will be multiple choice. You will have 3 hours to complete it from the time that you start. If you have accommodations through the Accessibility Center, now would be a good time to talk to me about it or just confirm things. I've got letters from the UAC for many of you, but if you haven't squared that away, I encourage you to take care of it. Let's see, what else? It will be open book, open notes. I realize that in order to use your book, many of you will need access to the internet because you use an ebook, so that's great. What I don't want is to have you copy the questions, post them on Chegg, and then wait for some random person on the internet to answer them. It's happened before, true story. It was, and in some cases, the answers that the people on Chegg gave them were incorrect, so sort of serves you right. Yeah, go ahead. If you take notes electronically, can you use them? Yes. So my goal here is to not penalize the honest people in order to try to weed out folks that want to cheat. So the way that you can sort of handle that is that you give people the ability to use whatever they want, but you give them a limited amount of time. I don't love that. Normally my exams are not timed, but it may be the best we can do. If the time limit is a particularly onerous burden to you, feel free to contact me and we can talk about it, but yeah. You should expect the kinds of difficulty of questions that are on the practice exam. However, realize that the exam is going to be next Tuesday, February the 2nd, Groundhog Day. Nice. So watch some Bill Murray in preparation for the exam. We probably are not going to get through chapter 4, all the way through chapter 4 like I had planned on doing. I will make sure the test doesn't cover anything we haven't covered by next Monday, okay? All right, any other things you want to ask? Go ahead.
So the exam will open on Tuesday and it will close?
The exam will open on Tuesday and close on Tuesday. You will have Tuesday to do it. Again, if that's a particularly onerous situation, please send me an email and we can talk about it. The limitations in time are designed to protect the security of the exam, but I also recognize that individual circumstances can be challenging. So anything else? All right. Well, we've been, oh, sorry, go ahead, Wallace.
We were just wondering how long they should plan.
Good question. How long should you plan? I believe 3 hours will be enough time to do it at least a couple of times. Average amount of time on these exams tends to be about an hour and a half. My sense is that there are folks that I know take longer than that on organic chemistry exams, but I think that in many cases, a lot of the time spent past 3 hours is in the valley of the shadow of death or the long dark night of the soul, staring at a question and pondering and second guessing yourself, which may or may not actually be useful. So I believe that chunk of time is a useful and doable amount of time. Again, if you find that that's not the case, or you feel in advance that that's going to be too little, you can let me know. But in general, folks have finished in plenty of time. Okay. Anything else? All right. Well, we've been talking about what makes a strong acid strong, what makes a conjugate base stable and less reactive. And this has been our way of trying to understand and get a feel for really how nucleophilic various molecules are and a way of ranking them. We've talked about a few different ways that you can stabilize electron density. The first was go ahead. The projector is not on. That's always fun. What didn't happen there? I forgot to do, okay. Thank you, actually. Sorry about that. One of these days, I'm going to get it. Okay, so we've talked about electronegativity, about how if you're in the same row of the periodic table and you compare which atom holds the negative charge in the conjugate base, that the more electronegative one will be the more stable conjugate base and therefore the more acidic acid. This is why, for example, HF is more acidic than methane by a crazy number of orders of magnitude if we look at their pKa's. And that is simply because the atom that holds the negative charge in the conjugate base is more electronegative, is fluorine, and can better tolerate that negative charge. The other illustration of this principle was really sort of alkane versus alkyne acidity. Alkanes aren't acidic enough for us to worry about in most cases. Again, pKa around 50. The alkyne, though, we do have some pretty useful and easy to get bases that can remove a proton from an alkyne. And the difference there was the hybridization of the atom that bears the negative charge in the conjugate base, where greater percent S character means that the orbital that holds that negative charge is lower in energy and therefore more stable. All right. We talked about delocalization a little bit in terms of size. So that was comparing HF, which is fluorine is very electronegative, versus HI, which is not. Iodide is not very electronegative, and yet HF is way, way, way less acidic than HI. And the reason for that was size, right? Iodide was our example of Bob the Sponge. Did I draw that in this class? No? Oh, I didn't do the sponge marble analogy. That was in the 1 o'clock class. Well, okay. We talked about how size, because iodide is larger, its valence electrons are spread out over space more, and that delocalization is stabilizing. Whereas for fluoride, the negative charge is localized on a very small atom and is not very spread out. If you struggle to see that delocalization of electron density can be stabilizing, it may help to think of this analogy. There are perhaps others, and I don't know how good this analogy is. In fact, it mixed results every year, but I keep doing it. So imagine a marble, and maybe it's one of those marbles that has the weird twisty things inside. And actually, maybe it's the Eye of Sauron or something like that. Imagine you put a drop of water, you have a little, I don't know, dropper like you would use in Chem 107 or something like that, and you put a little drop of water on top of that marble, and it just sits there and stares at you. And in contrast, what if instead of a marble, you happen to be a sponge that lives in a pineapple and maybe wears shorts? Need some brown color. Egregious wasting of precious classroom time on meaningless doodles. Well, you want to teach the class different? You go get a degree in organic chemistry. So there, whatever. So if, in contrast, if you're the sponge, we gotta just do it now. We gotta just commit. And the sponge have little holes here or there. And I don't know if SpongeBob is buck-toothed or not, but we're gonna. Is that tooth outside his mouth? That's kind of weird. There's his buck-tooth. Okay. Imagine instead you are a sponge and you get a single drop of water placed on you with one of those Chem 107 plastic droppers. Once you put the water in the sponge, can you tell where the water droplet is? Spread out through the whole thing, right? Similarly, iodide, which is large, is not as basic as fluoride because its electron density is spread out. It doesn't notice it as much. In contrast, fluoride, yeah, the negative charge is there, it's localized, it's obvious, and it's very reactive. So I don't know if that analogy helps or hurts, or if it was just a diversion, but that's one way you can think about it. Let's see. Another way you can spread out electron density that we've alluded to is through resonance. So compare the acidity of the following molecules. pKa for this carboxylic acid on the right is about 4. The pKa of the alcohol is 16. So 1 trillion times more acidic is the carboxylic acid. Why is that? Well, let's look at the conjugate base. If you draw the conjugate base, you can compare the atoms that bear the negative charge. Okay, they're both oxygen. Similarly electronegative, similar size. The difference is that just by moving lone pairs and pi bonds, we can delocalize the negative charge on the carboxylic acid oxygen onto the other oxygen. So we might say that that negative charge is held evenly between those two oxygens, whereas in this negatively charged deprotonated alcohol, we'll actually call that an alkoxide. And the negatively charged acid we'll call a carboxylate. That negative charge is localized on the alkoxide and is therefore more reactive. So resonance stabilization is one of the classic ways to be a very stable, unreactive, less reactive conjugate base, and then for your acid, the corresponding conjugate acid to be that much more acidic. There are other examples of this. I suppose we should talk about a regular hydrocarbon versus this allyl group. Conjugate base of a regular hydrocarbon is just a localized negative charge, pKa around 50. We've talked about the stability of the allyl anion, which can delocalize that negative charge via resonance. And that has a measurable difference in pKa. I don't actually know what the pKa of the allyl group is. I think it's around 30. All right. And it's because the negative charge on the conjugate base is delocalized by resonance. There are compounds similar to the allyl group, ketones and aldehydes. The pKa of a proton adjacent or alpha to a ketone is around 20, which is again 10 to the 30 times more acidic than your typical alkane. And the reason for that is if you remove the proton, the negative charge can be delocalized by resonance onto the oxygen. And now let's consider what's the difference, why the big difference in pKa between this proton, which is also alpha to a double bond, versus the proton that's alpha to the ketone. What's the difference there? Can you see any difference in the conjugate base that might explain why the pKa's are so different? Go ahead.
The electronegativity of oxygen allows for charge to be closer to oxygen, basically.
Okay, so yeah, the answer is, as was stated, in the resonance structure for the conjugate base of the ketone, part of that electron density can be on electronegative oxygen, which should be lower in energy than if it's just on carbon. Remember, in the allyl anion, the negative charge is just on carbon. So yeah, resonance gets you maybe a factor of 10 to the 20, and then maybe you get another factor of 10 I'm sorry, based on electronegativity. All right. So one of the things you want to be really good at as going forward in the class is recognizing resonance structures. I am notorious for drawing large and annoying structures on exams and asking painful and annoying questions about which atoms share the negative charge. So that's an example. You've got a negatively charged oxygen. It's adjacent to a pi bond. Which of the atoms shares that negative charge via resonance? To answer this question satisfactorily, it's useful to know how to convert one resonance structure to another. The way to not do this problem, by the way, is to try to do it all at once, which is, okay, I can move these here, and then I could move these where? Well, I could move them here or there, and then here, and then you get so mixed up that you have no idea what's going on. Some of you will still, despite this warning, will still attempt to approach the problem this way, jumping electrons around like crazy until you get lost and make a mistake. So what I recommend is that you go back to basics and do the negative charge lone pair two-step. Sounds like it should be from Texas. The lone pair state, maybe? Should we replace the star in Texas with lone pairs, maybe? Yeah. All right, we can move one of the lone pairs on oxygen to make a new pi bond between carbon and oxygen. If we stopped there, we would have too many bonds for carbon. So we have to take the pi bond and move it out to the other carbon that was involved in that pi bond. And then we will draw a new resonance structure. Now, at this stage, you may be panicking, thinking, come on, man, the exam's only 3 hours and you're wanting me to redraw the structure. We're not going to do it more than a couple of times. We're going to look for a pattern that's going to emerge as we consider the various possible resonance structures. So look at what this has told us. The negative charge can be on the oxygen, which we already knew, but it can also be on the carbon that is alpha to the carbonyl. There's sort of a pattern like we saw in the allyl anion. It can be on positions 1 or 3, but not on position 2, almost like the negative charge skips an atom. All right. Well, let's generate another one and see. We can move these lone pair electrons to form a new pi bond here. If we stop there, we'd have too many electrons around that carbon. So we move the electrons in that pi bond onto the far away carbon from that pi bond. And again, we could draw another resonance structure. Understand that on a multiple choice exam, you won't really be drawing anything for like credit, but you will need to have a pen and a paper or whatever so that you can work problems for yourself and make notes. What have we learned? Well, the alternating pattern has continued, right? We could be on oxygen or that carbon or that carbon. And so with that information in line, I can extrapolate what to expect. Skip a carbon, 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 and we're done. Okay, so a little bit of practice with resonance is probably a good idea until you can convince yourself of this sort of pattern and until you feel ready to answer this kind of question. Anything you want to ask about that? Yeah.
Just a quick reminder, what does it mean when a carbon is alpha to the oxygen?
Okay, great. The question asked was, what does it mean when a carbon is when some group is alpha to some other group. It's just sort of terminology that we use in organic chemistry. We say, okay, whatever a functional group is, maybe it's the ketone. The carbon that's adjacent to the ketone or the aldehyde or whatever is alpha. The next one would be beta, gamma, and if you really want to, you can go out from there. It's just a way of saying 1, 2, 3, and 4, but with different letters so that you sound cool because Greek letters are awesome. I don't know. What else? Yeah.
So would alpha just be like the prime carbon? Is that like the same way of looking at it? Or is it different?
Would alpha be what carbon, did you say?
If you're looking at, for example, DNA, there's like three prime carbons.
Oh, sure. Well, with DNA, that one is actually a bit more of a complicated story. The reason for the primes and whatnot in DNA is that the ring, the nucleobase ring has a different numbering system than the sugar ring. So I don't know why I'm doing this. I think this is adenine or something. I'm flexing my DNA knowledge. Yeah, so the ring has a numbering system with itself, 1, 2, 3, 4, 5, 6, 7, or so on. And then the ribose sugar has a distinct numbering system. So that's 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. And DNA is connected via phosphodiesters, 5 prime of one connected to 3 prime of another. I suppose we could use this alpha, beta, gamma stuff if we chose a reference point and we said carbon 2 prime is alpha to carbon 1 prime. It's just adjacent. Yeah. Did I miss another hand? Saw somebody? Yeah.
Why did you skip the carbon when you're like coming around with the electrons? Why did you skip some of them? Like, I don't understand why lone pair groups either.
Okay. It has to do with the fact that if we make a new pi bond with one of these lone pairs, and if we stopped there, what's the problem with that? Yeah, you got too many on this carbon. A Texas carbon is a carbon that is bonded to more than 4 things. It turns out they do exist in some strange circumstances, but for our purposes, no. Carbon will only be bonded to a maximum of 4 things. If you got 2, 4, 6, 8, 10 electrons around carbon, carbon can't accommodate that many electrons. Not even in the great state of Texas. And so that's why we call it Texas carbon, because it wants to be bigger, but it can't. And so in order to not break that rule, we have to take this pi bond and move it out there. And the effect of that is that the charge sort of skips one. So that's the sort of resonance explanation for it. The MO explanation for it really has to do with what we did with the allyl anion, where we saw that the HOMO skipped atoms. It was on carbons 1 and 3, but not on carbon 2. Remember us drawing something like that. 1, 2, 3. So that skipping pattern of where the negative charge can be is embedded in MO theory as well. Is that an aha moment?
Yeah.
I remember that aha moment when I was in this class in the year, what was it? 2000? Yeah, in the year 2000. I took 351 when I got back from my mission, fall of 2000 and then winter 2001. I can remember driving on University Avenue in my grandma car. It wasn't my grandma's car. It was a car that I had bought from a grandma when I got back from my mission. Mercury Sable, big boat. And we were driving by, I was driving with Amber who I was dating at the time, by the town center mall, and she thought I was spending too much time with my organic chemistry text. She worried that she had some competition or something, and the way I would work my schedule is I would study until 9 o'clock or something like that at night, and then I would run over to her apartment and we'd spend like 5 minutes together. I'd kiss her goodnight and then go home. And she asked me as we were driving, "Don't you want to spend more time with me?" And I thought about it and I said, on Wednesdays I could. And that was not the right answer. And it took me a little while to adjust, and I started studying at her place, which made it okay. And then when we got married, you're just together all the time anyway, so it wasn't an issue. But I still had to learn not to study. It was a great day when I got to grad school and there was no more homework, just research. It was so awesome. But anyway, you're on the early end of that story, so I'm sorry if I'm causing relationship troubles in your various experiences. I've been there, but apparently I don't care enough to not give you homework, right? So go ahead.
On that final resonance structure, yeah, that one right there.
Okay.
Is that a partial charge on every single second carbon?
Yes. So does this mean that the negative charge could be shared on each one of these that are highlighted? Yes. Now in practice, if you did the math and looked at the reactivity of this molecule, would you find that these carbons over here share the negative charge as much as the ones that are close to it? Probably not. Probably there's a tapering off effect, but we just want to recognize the possibility for resonance delocalization. Yeah.
So that would indicate that there's 10 resonance structures.
That would indicate, I don't know, did you count the purple dots? I didn't.
Yeah.
About, okay, yeah, there'd be 10 sort of different resonance structures where you move that particular negative charge around. Go ahead.
So that means this molecule would be highly acidic?
Would this molecule be highly acidic? Well, it would be more acidic than an alcohol. So there are molecules, I don't know what the pKa of the corresponding conjugate acid would be. What we've drawn here is a conjugate base, right? So we wouldn't be talking about the acidity of this molecule, we'd be talking about the acidity of its conjugate acid. The pKa of this proton on an OH group attached to a benzene ring is about 10, and that's about 1,000,000 times more acidic than just a regular alcohol. So yes, that option for resonance delocalization of the conjugate base does make the acid more acidic. I would predict that the acid we drew here, the conjugate acid of the base we've drawn here would be perhaps more acidic than just this one because there's more places to delocalize, but I don't know what the number is. All right. So we need to talk about one more thing of spreading electron density out. And this is kind of a tricky concept. It involves electronegativity, but not of the atom that bears the negative charge. This is where I need to look stuff up because I don't want to get the numbers wrong. Okay, that'll work. So alcohol versus trifluoroalcohol, where you've got 3 fluorines on a carbon adjacent to the carbon that has the alcohol. The pKa of the trifluoroalcohol is 12. So that's 10,000 times more acidic than the regular alcohol. And the reason is why? Well, if you look at when in doubt, when asked to rationalize acidity, always draw the conjugate base. In fact, if you're working on your mindfulness and you need a mantra to help focus your whatever, one of your mantras for this class, in addition to nucleophile attacks electrophile or homo attacks lumo, could be draw the conjugate base. Breathe in, draw the conjugate base, breathe out. What's the difference between these two conjugate bases? The one's got fluorines nearby. The negative charge is on oxygen in both cases. What do you suppose the fluorines do? Go ahead. Okay, so we know that fluorines are more electronegative than carbon, right? So we expect there to be a buildup of partial negative charge on each of these fluorines. One way we represent that sometimes in organic chemistry is with the following symbol, which is a dipole. The arrow indicates the negative end of the dipole and the cross indicates the positive charge end of the dipole. You've got individual bond dipoles in that direction. If you add them all up though, it creates a substantial partial positive charge on that carbon, which in turn makes that carbon in effect more electronegative, and it pulls on the electron density of the adjacent carbon, which in turn makes it more electronegative, and it pulls on the adjacent electron density of the oxygen. This kind of tug of war of electron density due to nearby electronegative groups is called an inductive effect, meaning that the electronegative groups induce delocalization of electrons through the sigma bonds. So this isn't resonance, but it's polarizing of the molecule that makes it a little less bad to have a negative charge on an oxygen. This kind of effect depends on proximity to the negatively charged oxygen. So as an example, you would predict that if you moved those trifluoro groups out another carbon further, this would be less acidic than alcohol 1, but more acidic still than alcohol 2. And that once you got out past a certain length, it wouldn't matter anymore. All right. So I think those are our ways that we rationalize our trends in pKa data. Now I want to give you just a little bit of background in terms of where pKa data come from, and then we'll talk about how to use it to make sensible predictions. All right. So acid strength varies over many orders of magnitude, as we've seen. And to keep everything straight, we sort of compare the acidity of each acid, which I'm representing as HA, with the acidity of hydronium. All right, so we have this equilibrium, and we measure this equilibrium constant for any acid that we can. It's more complicated than that, but it's okay if you think of it that way. Our equilibrium constant equals the concentration of hydronium, which we can measure, concentration of conjugate base of our acid, divided by the concentration of our acid and the concentration of water. Some of you are going to worry about that because I believe in general chemistry you were told that actually these concentrations are activities, and the activity of water equals 1. That's true, but we're not. But the approach I'm taking accounts for something called activity coefficients, and in any case gets us to right answers. So we're going to pretend that it's okay to put the concentration of water there. That being said, the concentration of water in pure water is like 55 molar. And so it basically stays constant during this equilibrium. Doesn't matter whether, it doesn't matter how much of our acid transfers a proton to water, the concentration of water is still basically 55 molar because there's a lot of water in water. That's an intelligent statement that you can now email your parents and tell them you're learning the great things in organic chemistry. There's a lot of water in water. So we'll actually take the water term and algebraically move it over to the other side of the equation to have KEQ times the concentration of water equals H3O plus times the concentration of the conjugate base divided by the concentration of acid. And this new constant, which contains the concentration of water in it, we're going to call Ka, the acid dissociation constant. So remember how we talked about how acids don't dissociate, that this process never occurs, at least not in water. We get the acid dissociation constant from this equilibrium, and the role that water plays is embedded in the acid dissociation constant. All right, but in chemistry, we sometimes don't like to do scientific notation if we can avoid it. And because these Kas vary over many orders of magnitude, we're just going to take the log of Ka. And then because we remember that minus RT log of K equilibrium is related to free energy changes, we're going to put a minus in front of that log Ka so that our value that we get tracks with free energy. That is, larger numbers are less stabilizing, lower numbers are more stabilizing. So we're going to define that term, the minus log of Ka, pKa. And we call it that because if you look at what taking the minus log on the other side of the equation does, I did promise you that the math would be easy. I am sorry, you're going to have to maybe remember or accept on faith some properties of doing math with logarithms, which I cannot prove to you and only sort of know how to use. But this is what Google is for. So apparently in logarithms, we can separate out products as sums of logs. So minus log of H3O plus minus log of A minus over HA. Does that look reasonable? I haven't broken any laws. Oh, hold on. Minus log of hydronium, that's pH, right? So pKa equals pH minus log of, and actually, if you prefer not to subtract things, you can change this to pH plus log of conjugate acid over base. Okay. Basically, pKa tells us how strong an acid is. If an acid is strong, there should be more hydronium and more conjugate base. That should lead to larger values of Ka, and therefore smaller or more negative values of pKa. All right. And by pushing the algebra a little bit further, we've actually derived the Henderson-Hasselbalch equation. In general chemistry, you use this probably to talk about preparing buffers. You learned that if you know the pKa for a particular acid, and you mix the acid and its conjugate base in the appropriate ratio, you can prepare a buffer that has a specified pH. And this is true, and it's very useful. Any of you that work in life sciences or biochemistry labs will have had or will have the experience of making a buffer, and you do this math to figure out how to do it. Actually, you Google a web page that does the math for you. You tell it what pH you want and what acid and base you want, and it tells you how to mix them together. And buffer making is great, but it turns out that many of the molecules we're interested in biology and in organic chemistry are present in concentrations that are much lower than the concentration of the buffer you might be preparing. Who knows what the pH of blood is, or serum? 7.4, 7.2, something like that, I don't know. We need a pH strip and a knife, and we can find out. Should we try that? Your blood, I believe, is buffered mostly by an equilibrium between carbonate and bicarbonate or something like that. The concentration of a lot of biomolecules, of proteins and other biomolecules in your serum and in your cells is maybe micro or millimolar, whereas the concentration of buffer is hundreds of millimolar. So in many cases in chemistry, or at least in OChem and biochem, the biomolecules we put into a solution aren't going to change the pH of the buffered solution. Rather, they're going to be defined by the pH of the buffered solution. Here's what I mean by that. Imagine I have a beaker. Imagine I have a beaker. Not the kind from the Muppets with the eyes and the nose and the me. That was, I'm sorry, it was terrible, terrible. Throwaway joke. I've got a beaker with a solution, and suppose that pH, we just buffer it at 7. And then suppose we put in a biomolecule like some kind of protein, maybe bovine serum albumin or something like that. And that protein is covered with groups that have pKa's that can be either protonated or deprotonated. For example, there's an NH2 group maybe on one of these. There's a carboxylic acid group over here. There's maybe some other, I hate this one, guanidine group. These are actually amino acid side chains. And we ask, what is the acid equilibrium state of each of those groups in this pH 7 solution? So let me show you how you figure this out. All you need to know is what the pH is, and then what the pKa of a particular group is, and then you can make the decision. All right. We can rearrange this expression if pKa minus pH equals log of acid form divided by conjugate base form. So if this side of the equation is positive, and I suppose we'll just use greater than 0, that means the concentration of HA is greater than the concentration of A minus. That makes sense? What the logarithm of what number equals 0? 1, right? So if the concentration of HA and its conjugate base are equal, then the left-hand side of our equation is equal to 0. If the left-hand side of our equation is less than 0, then that means that the base form dominates over the acid form. All right. So now all you need to know is what is the relevant pKa to consider. Let's start with the carboxylic acid. You could look it up in a pKa table. Carboxylic acids, we're starting there because they're terribly easy to recognize. pKa of the carboxylic acid is 4. So do some math. 7 minus 4 is, no, it's 4 minus 7, right? pKa minus pH. That means that our left-hand side of the equation is negative. So which form of the carboxylic acid dominates, the acid or the conjugate base? Conjugate base, right? Has to be, because 4 minus 7 is -3. That means there's 1,000 times as much base as there is acid. So what that means is at pH 7, this carboxylate is going to be deprotonated or negatively charged. Okay? All right. See how we made that jump? Let's look at this group here. Amino groups are interesting because amino groups have a couple of different acid-base equilibria they can engage in. The neutral amine itself could get deprotonated to become RNH-. minus, that pKa is 38, pretty unfavorable. However, the neutral amine itself is the conjugate base of a positively charged protonated form, the ammonium. You got ammonium to amine, and then amine to, this is actually called, I don't know, amide. The pKa on top from the ammonium, positively charged ammonium to the amine is 11. All right. People always struggle with this because they forget which pKa goes, which number goes with which state of the amino side chain. Some people will look at this and say, oh, amines have a pKa of 38. 38 is way larger than 7. Therefore, that proton is still on and the amine form dominates. I agree with you that there is no amide in solution at pH 7, but there's also no amine because the amine itself is the conjugate base of an acid whose pKa is 11. At pH 7, 11 minus 7 equals 4. That means there's 10,000 times as much ammonium as there is amine, which means at pH 7, what should this side chain look like? Should it be neutral? Should it be positively charged? Should it be negatively charged? Positive, right? You can tell that because its pKa is higher than the pH. When pKa is higher than the pH, that proton is still on. So don't make that mistake. Some of you might anyway. I've warned you. Some of you might make that mistake anyway, but don't do it. Alcohols have a similar situation. Alcohol going to negatively charged alkoxide has a pKa of 16. So at physiological pH, that proton is still on, but the alcohol itself is the conjugate base of the protonated oxonium ion, which has a pKa of -2. So you tell me, for an alcohol at pH 7 in water, what should its state be? Should it exist as oxonium, as alcohol, or as alkoxide? At pH equals 7. If pH is greater than pKa, that proton should still be on. Wait a minute, did I say that wrong? I did say that very wrong. Oh my gosh. All right, well, I had it right in the notes, so, okay, let's write it out in words. If pKa is greater than pH, the proton is still on and the HA form wins or dominates. Okay, I think I said it right there. This is what I mean. If I said it wrong earlier, I apologize. I sign here in my own hand and in my own blood that that is the right answer right there. So what form of the alcohol should be dominant at physiological pH or pH 7? The alcohol, right? It shouldn't be the alkoxide. That proton is still on. It should also not be the oxonium because at pH 7, that proton should be off. All right. That's not necessarily, thinking it through this way is not necessarily how we've done it in the study guide, but it will be important to you in future life science classes if you choose to work in a life sciences or biochem lab. And it will come up again when you take 352. So I wanted to make sure you had it there. We will probably need a couple more minutes next time to finish up chapter 2. So I'll go ahead and kick back the study guide to due date. We'll get to what we get to before the exam and we'll move on from there. So thank you and have a great afternoon.
Hey, Professor, can you hear me?